So thanks everyone for coming. I'm very glad to be here and to present to you an outline of my job market paper termed Comparative Rationality. Okay. So in economics in general, and in choice theory in particular, we say that choices are rational whenever we can account for them by the maximization of a complete and transitive preference relation. That is, from every menu, we observe the agent choosing, the agent maximizes the same preference. Okay. Throughout the talk, this is all I mean by the term rationality. So I will use the term rationality and preference maximization interchangeably. Now, as we all know, rational choice underlies most of applied economics. Economic agents maximize utility over different domains, and therefore, the welfare and policy implications of these applied models rely on this behavioral foundation. However, choices are not always rational in this sense, right? We have a bunch of now experimental evidence that people violate rationality in different domains. Now, and we also have a list of reasons for why. We have intransitivities in choices, preferences can be incomplete, people can make mistakes, there might be choice overload, a host of behavioral biases like framing effects, attraction effect, compromises effects. People might face unobserved constraints like social constraints or attention constraints, or they might be using different choice procedures altogether, and their choices might not be rational, and the resulting choices from these procedures might be incompatible with rationality. So a key question is then, when are choices sufficiently rational? That is, when does the preference maximization model provide a sufficiently adequate description of behavior? To answer this question, we need to qualify, or we need to give a meaning to what sufficiently means. And to do that, we need to come up with ways to measure incompatibility with rationality, right? So there is a whole literature that the basic question they ask is how to quantify the incompatibility of the choices we observe from the choices that are generated by the maximization of a complete and transitive preference relation. The standard approach to this question relies on indices of incompatibility. So what is an index of incompatibility? It assigns to the choices of a person over a certain collection of menus a number. Since we're talking about indices of incompatibility, the higher the number, the less rational choices are. That is, the more incompatible they are with preference maximization. If I want to make comparative judgments of rationality, I simply compare these numbers. And the person which has the higher number is the one which is the less rational. This is the standard approach. Here are some papers that, beginning with Afriat, contribution in 1973, propose new indices of incompatibility with rationality. I will skip the literature review in the interest of time. Now, notice one thing, the index approach compares choices indirectly. By that I mean it compares choices by comparing the number it assigns to them. Moreover, it assumes that any pair of choices that you give me can be compared, right? I think that completeness is a strong assumption, and it should be seen more as a lofty goal. That is where you want to arrive, because it's clearly desirable to be able to compare any two choices, but it shouldn't begin by assuming that you can. So with this in mind, I propose a different approach to the topic, which is the partial ordering approach. So what I will do is I will introduce a criterion for making comparative judgments of rationality. That is, give me the choices of two people. The criterion will say when one choice is at least as rational as the other. However, the criterion will not be able to compare all the pairs. The pairs of the comparisons that the criterion can make, I'll try to convince you that they are in a sense obvious. And the choices that the criterion cannot make are in a sense difficult. If I can convince you of that, then it's very natural to use this criterion as a mechanism for selecting indices, right? We will want that indices of incompatibility agree in the obvious choices while being free to disagree in the non-obvious ones. Okay, so this approach, although it's new in the domain of comparisons of rationality, is not new in economics in other fields, right? So think, for instance, of the Pareto ordering to measure social desirability, or the first order stochastic dominance to measure desirability of lotteries, or the Lorentz ordering to measure inequality of income distributions. So to illustrate my criterion, I will go through an example where we'll try to rank the rationality of choices, and this will illuminate what I am doing. So the example is fairly simple. We have 5 friends, and we want to rank their rationality in a certain domain. This domain is composed of 3 alternatives, which we will call A, B, and C. So I'm going to ask them, to the 5 friends, what they would choose from all the menus that you can see in the first row here. So for instance, in the menu ABC, friend 1 replied that he would choose C. Friend 2 said, look, I'm equally well with A and C, and so forth. So we fill out this table. Now let's begin by analyzing their choices from pairwise menus, that is, from menus with 2 alternatives. If we check, you will see that the choices of friends 1 to 4 are compatible with rationality, that is, with the maximization of a preference relation. For instance, the choice of your first friend can be explained by saying that he strictly prefers C to A to B, and C to B, right? The same thing for a friend 2, he's indifferent between A and C and prefer both to B. Friend 3 has the same preferences as friend 1. Friend 4 prefers C to B to A. However, your friend 5 has a cycle in pairwise menus. Okay, so far what we have learned is that your friends 1 and 4 in pairwise menus are compatible with preference maximization, while your friend 5 is not. But notice one thing. Once we know what your friends 1 to 4 chose from the pairwise menus, we can try to predict what they would choose from the menu ABC, if they are preference maximizers. So your friend 1, we would predict that he chooses C. The same thing for friends 3 and 4. And for friend 2, we would predict that he would be indifferent between A and C. If we go back to the full choices, our predictions would be correct for friends 1 and 2, but it would be incorrect for friends 3 and 4. So far, we have a very coarse ranking of rationality. That is, friends 1 and 2 are perfectly rational and are strictly more rational than friends 3, 4, and 5. But this is too coarse. Let's try to do a bit better. So let's compare friends 3 and 4. Notice that the only difference in their choices is from the choice they make from the menu AB, where your friend 3 chooses A, your friend 4 chooses B. Your friend 3 displays a violation of rationality in their choices from the menus ABC and AC, right? He reveals that he strictly prefers A to C and then C to A. Notice that your friend 4 shares this violation as well. But when choices change from A to B, this generates an extra violation of your friend 4 on the menus ABC, AB, a violation which is absent from your friend 3. So I think that in this case, it's fair to argue that your friend 3 is more rational than your friend 4. Let's try now to compare friends 3 and 5. Again, their choices only differ from in the choices they make from the menu BC, where your friend 3 chooses C, your friend 5 chooses B. Again, they both share the violation that your friend 3 has. However, when the choice changes, this introduces a cycle in pairwise menus for friend 5, a cycle which is absent from the choices of your friend 3. So again, I think it's fair to say that your friend 3 is more rational than your friend 5. What about your friends 4 and 5? They both share this violation here, right? In the menus A, B, C, and AC. However, your friend 4 has a violation in his choices from the menus A, B, C, A, B, while your friend 5 does not. At the same time, your friend 5 has a violation of rationality from pairwise menus, and violation which is absent from your friend 4. So then how should we rank these two types of violation? At this level of generality, I suggest that we should simply suspend judgment, right? So this is the ranking we would get in this example. Any doubts about the example? So let me try to illustrate what emerges from this example. What is the criterion that emerges? So friend I would say that friend I is at least as rational as friend J, when for each subcollection of the menus that I observe, whenever friend I violates rationality in the subcollection, friend J will also violate rationality in the subcollection. That is what I'm doing a subcollection by subcollection comparison of violations, right? This is the basic idea of my approach. It's very simple, and I hope to prove you that it's interesting. Any questions so far? So now I'm going to go to present the basic notations and definitions that I'll have for the rest of the talk. And today, because of time constraints, I will only be able to address one issue, which is what kind of indices of incompatibility, that is, what kind of indices preserve my ranking? This is the question that I'm going to try to address today. But towards the end, I'll tell you more of the other things I do in my job market paper. So here's the setup. It's fairly simple. We have a set X, which is the set of alternatives. A collection script A, which is the collection of menus that we observe people choosing from. I will call the pair X script A a choice space. And a choice correspondence on this choice space is simply a correspondence that for every menu returns a non-empty set of alternatives, which is the set of alternatives that we interpret as being chosen by the person. By this notation here, script C of X of script A, I will denote the set of all choice correspondences on this space. This is the notation. Just so that we are all in the same page for what rationality means, let me formally define it. Usually when you define rationality, you define it with respect to the whole collection of menus that you observe. So I will slightly generalize it to rationality in a sub-collection of menus. So I will say that a choice correspondence C is rationalizable on a sub-collection script B if I can find a complete and transitive relation over the elements that belong to at least one menu of the collection script B, such that for all menus that I observe that are in script B, the agent maximizes the preference, chooses by maximizing the preference in the menu. This is what rationality means here. Right. Now we are ready to formally state my rationality ordering. Give me two choice correspondences, C1 and C2. I will say that C1 is at least as rational as C2 if for every sub-collection of menus that I observe, if C1 cannot be rationalized on that sub-collection, then C2 can also not be rationalized in that sub-collection. Or by the counter positive, for every sub-collection, if I can rationalize C2 on it, I can also rationalize C1 on it. If that is the case, I will use this notation here to express this relation. Okay, so it's a rational, I will call this the rationality ordering. Now, when is it the case that C1 is more rational than C2? When C1 is at least as rational as C2, and there is one sub-collection where C1 is rationalizable, but C2 is not. When are they equally rational? When they violate rationality in the same sub-collections, or equivalently, when they are rational in the same sub-collections. And when are they incomparable? When I can find two sub-collections, script B1 and script B2. In script B1, I can rationalize C1, but not C2. And in script B2, I can rationalize C2, but not C1. This is the basics. Now, one more piece of definition that I will need. What is an index of incompatibility? For this talk, I will define an index of incompatibility as any function that maps choice correspondences defined over the same choice spaces to the non-negative real, and that will assign a number of 0 to a choice correspondence if and only if it is rationalizable. Right? This is the only restriction. So let me give you a very trivial index. If a choice correspondence is rationalizable, I assign a number of 0. If it is not, I assign a number of 1. Very simple. And this will qualify as an index of incompatibility. Now, when does an index preserve my rationality ordering? That is, when does it extend my rationality ordering? When it does so, I will say that the index is consistent, and it will be so whenever my rationality ordering says that C1 is strictly more rational than C2, then the index assigns a strictly smaller number to C1 than to C2. And when they're equally rational according to my rationality ordering, the index assigns the same number to both. Some indices in the literature are, in fact, none of the indices that I could find in the literature, to my surprise, is consistent with my rationality ordering, right? But there are some which are weakly consistent. Okay, weakly consistent is very weak. For instance, the only thing that I claim is that if C1 is at least as rational as C2, the index must assign a weakly smaller number to C1 than to C2. But what might be the case? My rationality ordering says, look, C1 is strictly more rational than C2, and the index assigns the same number to both. So an index which is weakly consistent is the trivial index I just gave you. Right? The trivial index is weakly consistent with my rationality ordering. So weak consistency does not say much, but it still limits the kind of disagreements that can occur. Right. So in the rest of the talk, what I will do is to characterize when an index is consistent with my rationality ordering, right? Since I told you as a spoiler that none of the existing indices are, the natural question is what kind of index would be? So to do so, I will propose a different way of looking at my rationality ordering, which uses a particular notion of predictive errors. Now, to introduce this notion of predictive errors, let's go back to the example a bit and think how we reasoned in the beginning, right? So take C as being the choice of some friend, let's say friend 1, script B to be the collection of pairwise menus, and A to be the menu ABC. So in the beginning of the example, we went to pairwise menus, checked if choices were consistent with preference maximization, and then if they were, we'll try to predict what the friends would choose from the menu ABC. If my friends get it right, that is fine. But if I get it wrong, my prediction, then I will say that A is a predictive error based on the preferences revealed on script B. This is the idea, right? So let me formally state that. I say that A is a script B predictive error on C if C is not rational on the collection of script B after I add the menu A to it. So what is the intuition? I go to script B, I elicit preferences. This imposes restrictions on what can be chosen from the menu A. When I go to the menu A, these restrictions are contradicted. And then A is a script B predictive error on C. However, sometimes for a given collection script B, we might not be able to elicit preferences there because the choices are not rationalizable on that subcollection, right? In this case, you can think as a convention that everything is a script B predictive error, right? Because if I add any menu to a collection which is not rationalizable, the collection remains non-rationalizable. To differentiate this case from the case where C can be rationalized in the subcollection, I will say that when C is rationalizable on script B, I'll say that A is a proper script B predictive error on C. Now, to systematize these predictive errors associated with the choice correspondence, I define this predictive error map. What it does is to every choice correspondence, it maps a different function, and this function maps subcollections of menus to the set of script B predictive errors based on that subcollection. This is what the predictive error map does. Let me just give you an example so that we can fix ideas and get familiarized with the notation or with the logic of the exercise. So suppose X, as before, has 3 elements, and suppose that script A now has only 3 elements. We observe choices from the menus ABC, from the menu AB, and from the menu AC. For ease of notation, define 3 subcollections. Script B1 is a collection whose only menu is ABC. Script B2 is a collection composed of 2 menus, AB and AC. And script B3 is a collection composed of the menus ABC and AB. Now consider the following table. Disregard for now the 3 last columns here, and let's focus on the 3 first columns. We have 3 choice correspondences, C1, C2, and C3. C1 always chooses A. C2 chooses A from ABC and AB and C from AC, and C3 chooses A from ABC, B from AB, and C to AC. So it's clear that according to my rationality ordering, C1 is strictly more rational than C2, which is strictly more rational than C3. Right? Now let's try to compute our predictive error map in the subcollection script B1. How would we reason? We go to script B1, right, and elicit preferences. For all choices here, C1, C2, and C3, we would infer from his choice from the collection ABC that they strictly prefer A to B and A to C. Therefore, we would predict that from the menus AB and AC, A should be chosen, right? So we would, for C1, we would make no mistake because it does choose A on both collections. So the set of script B1 predictive errors for C1 is empty. For C2, we would make one mistake from the choice of the set AC. So there is one, AC would be a predictive error here. And for C3, we wouldn't get it wrong in both AB and AC. So then we have these 2 are predictive errors. So what do we begin to conjecture? It seems that as choices become less and less rational, the set of predictive errors begin to increase, right? And it turns out that this is true in a major way and provides a different characterization of my rationality ordering. So I introduce it as saying, look, I'm comparatively checking for violations of rationality, but it turns out that this can equivalently be stated as I'm comparatively checking for predictive errors. That is, C1 is at least as rational as C2. If for every, the equivalence between 1 and 2 says that C1 is at least as rational as C2, if for every subcollection of menu script B, whenever I have a script B predictive error for C1, it will also be a script B predictive error for C2. Okay. However, what the equivalence between 1 and 3 says is that I can focus only on proper predictive errors. That is, I can focus on subcollection script B, where both C1 and C2 are rationalizable, so our intuition about what a predictive error is correct. So this is the takeaway of the proposition, right? Now that I have this result, I can finally provide an intuitive characterization of when an index of incompatibility is consistent with my rationality ordering, and also when is it weakly consistent. Okay? I will characterize both. So to do so, I will introduce this partial order here over the range of my predictive error map. I will call this partial order the generalized inclusion partial order. So I say that theta C1 is generalized included in theta C2 if every script B predictive error of C1 is a script B predictive error for C2 for every subcollections of menus that I have. With this definition, I have that I can now state that previous proposition says that C1 is at least as rational as C2 if and only if theta C1 is generalized included in theta C2. But now you can begin to conjecture or to that if I want to find indices of incompatibility that are consistent with my rationality ordering, I need to find indices that increase when the set of predictive errors increase as well. And it turns out that this is true in a major way. That is, any index of incompatibility that is consistent with my rationality ordering can be interpreted as monotonically aggregating predictive errors. So the proposition is an index of incompatibility is consistent with my rationality ordering if and only if I can find a function g, which acts as an aggregator that maps the range of my predictive error maps to R plus, such that first I can decompose the index in two parts. I first apply the predictive error maps, and then I aggregate it with G. And this G, the key property it has to satisfy is 2, right? As these predictive errors increase, and in at least one dimension it strictly increases, then the aggregator has to strictly increase as well. If I want to get a characterization of weak consistency, I just substitute this strict increase here by a weak increase, and that is all I need. Finally, the third question is the third condition is just a normalization, right? I say that I will assign a number of 0 to the image of choice correspondences, which are rationalizable, because that is how I normalize the indices of incompatibility. So this is not. So this is the characterization. Okay, so I'm almost in the 25 mark. So let me just give you a brief outline of the remaining results of the paper that I won't be able to present today. As I said, none of the existing indices of incompatibility that I could find are consistent with my criteria. Although some of them are weakly consistent. In particular, there is a very famous index in the literature called the Hauptmann-Max index, which satisfies these weakly consistent requirements. So what do? I propose a method to build consistent indices from weakly consistent ones. So I can take the Hauptmann-Max index and then transform it in something and then adjust it so that it becomes fully consistent with my rationality ordering. This method is fairly general and allows me also to assign weights to different types of violations. So for instance, you might think that a violation of transitivity in one pair is more serious than in another pair. This method will allow you to incorporate that. I use this method to propose 2 new indices of incompatibility. That is the probability index and the average Hauptmann-Max index. I also show that my rationality ordering can capture the severity of violation in well-known models of choice. What do I mean by that? So suppose that I take the choices of 2 people that, although they cannot be explained by the maximization of a complete preference relation, they can be explained by the maximization of an incomplete preference relation. Now, suppose that the choice of one person is at least as rational as the choice of the other, according to my rationality ordering. Then I can show that the person which is at least as rational under some conditions will be able to be rationalized by a more complete preference relation than the one which is less rational. I have similar results to other models of boundary rational choice. I drop transitivity, I drop menu independence, I drop the maximization assumption, and also to models which subsume the preference maximization model, but are not so closely related, like the rational shortlist method model of Manzini and Mariotti, and several others in the literature. To end, I then go to a choice elicitation experiment. That is an experiment that elicits choices, and I use the data generated in the experiment to compare my methods with previous methods in the literature. What do I find? The Hauptmann-Max index, which is one of the most used indices in this literature to control for violations of rationality, disagrees with my rationality ordering in 22% of the comparisons that my rationality ordering can make. And I show that this has implications to the degree of rationality you would impute to choices. I also showed that the Hauptmann-Max index is far less discerning than the two indices I propose. In particular, in the data, the Hauptmann-Max index only has 6 levels of rationality. There is the rationality ordering it induces on choices only has 6 indifference classes, while the probability index and the average Hauptmann-Max index have 62 and 64 levels of rationality. That is, they are far more discerning than the Hauptmann-Max. And finally, the two indices I propose disagree very little with each other, which is good because the average Hauptmann-Max index is computationally costly to calculate, while the probability index is not that much. And let me just end the presentation with the takeaway. I have introduced a new approach to comparisons of rationality, which are based on an intuitive criterion for comparative judgments. The criterion can be used for index selection, as I said. The criterion admits 2 equivalent interpretations. I'm comparatively checking for violations, or I'm comparatively checking for predictive errors. And an index of incompatibility is consistent with the criterion when I showed you that when it monotonically aggregates predictive errors, but when predictive errors increase, that means that new violations are being introduced to the data. So it must increase with the introduction of new violations as well. And that's what I have for today. Thank you very much for listening.
Thank you, Mauricio. We have 1 minute for questions. Are there any questions? I do have one, it may be a dumb one, but your way of comparing rational agents, the alternative set allows for absolutely any set. So in a sense that if you have a subcollection of a choice for which there can be no rationalizable choice, the choice correspondent is non-empty, then we cannot then we cannot say whether that agent is rational or not, or we are restricting the alternative set to be a finite or anything for which we know that there will be a choice correspondent, choice correspondence well defined.
Well, so although the sets that I'm considering are completely arbitrary, when you impose that the choice correspondence is non-empty, you're kind of imposing that if the choice is infinite, you need some form of compactness or continuity of preferences for it to be empty. But in general, the approach works for any set where choices are non-empty, right? That is kind of the idea. So this generality is kind of good because experimenters or researchers usually do not have control on what sets you can ask for people to choose from. So my approach needs to apply regardless of the choice sets that are given. So I think it's kind of
right.
But thank you. Yeah. So I'll give the floor to Caio, I think.
Okay, so can you hear me? Yeah.
Yeah. So we can see your screen as well.
Okay,
Good.
perfect. I had some problem during the previous talk with my computer. If that happens again, I think Anna is here. She can help me out a little bit, but let's hope it doesn't help. It doesn't happen. Okay. So this paper I'm presenting is called Competing for Stock Market Feedback. It's a paper joint with Anna. This paper is still very preliminary and is going through sort of a major revision right now. What I'm presenting today, it's not still the revised version. So this is just to say that the marginal utility of any comment you have is high at this point. Okay, so this paper starts with a very old idea in financial economics, which is that financial markets provide information about economic fundamentals. The idea here is very simple. You have a bunch of people. Some people have good news about a firm. Some people have bad news about a firm. Some buy stock, some sell the stock. On average, prices should reflect sort of the average belief in the population. And if that belief is correct, that's very good information. That is information that aggregates, that's a piece of the price aggregates the information of several people in one number, right? And if that's the case, firms may find it useful to use that information to guide their decisions. And then there's this whole literature on feedback effect that emphasizes this, that now if firms use the information contained in prices to guide their decisions, prices did not only reflect the fundamental of the firm, but through this informational channel, they may also affect firm decisions and ultimately affect firm fundamentals. And the classical example here in this literature is the merger and acquisition decisions, which often after a rumor of an acquisition, if firms observe a negative market reaction, they give up that acquisition or that merger. But there are also some more recent, both empirical and theoretical work, saying that firms often take actions to try to change how much information is aggregated in their price, to try to change how much they can learn from the stock market. And here I cite 3 papers. The first one is this Lilium Sun paper, the ER, that shows that firms adjust managerial compensation as a response to this informational channel. I have a paper with Anna, it's a theoretical paper where we look at capital structure decisions. And there's also this nice Foucault and Fraser paper that look at product differentiation. But the point I want to emphasize here is that firms, they actively try to shape the information environment. They actively make corporate decisions to try to change how much information is aggregated into their prices. So what we do in this paper? We first start from this observation that firms often have their stocks traded in the same venue by the same pool of speculators. And these speculators, they have limited potential to trade on information due to several frictions that may be present on those markets. So these guys can have wealth constraints, they can have limited attention, pick your favorite. Okay, the point is, these guys, they cannot trade all securities, which means that if one firm is able to attract more firm trade to its own stock, it may mean less firm trading to other stocks in the market. Okay, so we start from this very simple observation, and we want to ask here, okay, what kind of distortion arises when firms have to compete, or they want to compete, to attract firm trading to their stock? How does this competition for trading, from firm trading, is going to ultimately affect stock market potential to aggregate information and to improve the real decisions of firms? Okay, so that's where we're going right now in this paper. So let me give a brief overview here about the model we proposed to answer that kind of question. So let me see here if there's something in the chat. No. Okay. Oh, sorry, what happened here? Okay, so let me give you a brief overview of the model we proposed to answer the kind of question. So we propose a model in which there are many firms that are publicly traded that try to learn from the market. These guys have some uncertain investment opportunity and they want to learn about it looking at the prices. We have speculators that are subject to frictions, and they're going to have to endogenously choose where to allocate their limited trading capacity. Okay, so they're going to choose which stocks to trade. And then we're going to have firms that are going to make some decision ex ante to try to boost how attractive their stock is to traders. Okay, so here in the model I'm presenting today, it's going to be a managerial compensation scheme. Basically, the firm is going to choose some investment policy at the end of the day. Okay, but you can think about this more broadly, actually. And this is going to affect how firms react to market activity, and it's going to affect speculator incentives to trade. Okay, and that's going to be the margin that firms are going to use to compete for market feedback in the model. So I have some weird thing here on my slides, but that's okay. So let me give a quick preview of the results. This competition for market feedback, the first result, which was very surprising to us, is that this competition effect may completely shut down the benefit of learning from prices. Okay, this is in the following sense: we're always going to have an equilibrium in which firms do not react to information, even though stock prices are going to be very informative about the fundamentals of firms. Okay, so there's equilibrium is always going to be there. And here we make this distinction that revelatory efficiency, the extent to which prices contain useful information for decision makers, does not imply real efficiency, the extent to which this information is used by firms to guide your decisions. Hopefully, I'm gonna be able to explain you well why this happens. Even in equilibria where you can still learn something, you can still use this information to some extent, still you're not gonna use it as well as you could. Okay, there's still gonna be this inefficient in the use of information obtained from the market. We have something where we call the commitment paradox, which basically says that I'm going to show in equilibrium firms are not going to maximize shareholder value. They're going to choose not to maximize shareholder value exposed because that's going to affect how much information they get from the market. And I'm going to show you that they would like to collectively agree, let's say, no, let's simply maximize shareholder value, would all be better off, but in equilibrium that doesn't happen. And this, certainly I won't have time to go through this, but we also discuss a little bit IPOs. And we show that when the decision to be listed or not of those firms is endogenous, they choose it. In equilibrium, we have the too many firms end up going public, but I won't have time to discuss these results, most likely. Cool. I'm going to skip the literature review because otherwise I won't be able to present the results. Cool. So let me start with the model. I'm going to have a number J of firms larger than 2, larger or 2 or larger than 2, and the cash flow of the firm depends on 2 things. One, it depends on an exogenous firm-specific fundamental that can be low or high. It's this theta J here. 2, it's going to depend on the investment decision of the firm, which here is a binary decision 0, 1. Okay. If the firm undertakes investment, then the cash flow is state dependent. So if you invest and the state is high, you get VH, but if the state is low, you get nothing. Okay. If you do not invest, you get a given fixed amount V0, which is larger than 0. Okay. So if you think the state is low, you do not want to invest. If you think the state is high, you want to invest. For technical reasons here in this talk, let's assume VH is larger than 2 times 0, which means that ex ante, if the firm had no information at all, she would undertake that investment. Okay, that simplifies things a little bit for us. Cool. What is the ex ante action of the firm? Here I'm going to emphasize this compensation contracts. Okay, but at the end of the day, what I'm emphasizing here is that the firm commits to some investment policy. So how are we going to think about it? We have some controlling shareholders at the firm at date 0.
Can I ask us a quick question about your payoff specification in the previous slide? I just want to make sense of it. So because here, so the way I understand that if you do not invest, then you have this positive payoff regardless of the state, is that this is an alternative investment opportunity that you're missing and this generates some sure cash flow. Is that how I should think about it?
Exactly.
Okay.
So this is like status quo, and here is, okay, let's buy this firm, let's do this merger, let's do something different.
Okay. But
Thank if you go wrong.
Okay.
Anyway, if you want to ask questions during the presentation, it's fine. I prefer to answer them during the talk than at the end. So let's move on. Okay, cool. So the firm then is going to offer, we're going to have some controlling shareholders at the firm, and they're going to offer this contract to their manager. Okay. And basically, the manager is going to have some. So the manager is going to have some this managerial compensation scheme given to them, and then after he observes market activity, he's going to decide whether or not he undertakes this investment. So the firm delegates the investment decision to the manager to maximize his expected compensation. Okay. At the end of the day, what matters here is that the contract that the firms choose is going to affect the minimum probability that the manager assigns to the state high so that he invests. Okay, so the manager is going to invest always whatever he thinks the state is high probability larger than this gamma J here. but this gamma and J depend on the type of contract this manager has. Okay, so for this talk, let's just think that the firm, at the end of the day, she chooses the so-called conservatism measure of the manager, which has increasing function of this probability he is going to require to invest. Okay, and the way she does that is by changing his contract. Okay, so you could think of other margins, but I don't want to get into that. So the controlling shareholders is going to maximize ex-ante firm value, which is just going to be, you can think that you always get V0, but if you invest and you are successful, you get some extra term here. But if you invest and you fail, you lose your V0 you have guaranteed. And here I'm already using that you always need to pay a compensation contract to the manager that gives him his outside option. So this U lower bar is the outside option of the manager. Okay. What is the financial market here? So the financial market here is quite of standard. We don't do anything very different from what the literature usually does. So we have a continuum of risk neutral sophisticated speculators. This is the mass of sophisticated speculators I have in the market. I'm going to have noise traders, and I'm going to have a competitive market maker. After observing the firm conservatism ratio, the investment policy of the firm, each speculators decide which stock to learn about, okay, and then how much to trade on that stock. Once you choose to learn about a stock, you get a signal that can be low or high. And that signal is correct with probability lambda, which is larger than 0.5. So the signal is informative about the fundamentals of the firm. Maybe wrong, but on average, there's a continuum of those guys. If you could know the proportion that got the signal, you would know the fundamental. All right. But of course, because of the noise traders, you're not going to be able to do it. Cool. What are the trading decisions then? The speculators.
So just sort of a clarification question. So you have this finite set of firms. They simultaneously choose the conservative index, and then trade takes place, and then the managers make investment decisions.
Exactly. That's the model. Yes.
Okay. Thank you.
You're welcome. Okay, so we're going to have this speculator that's going to then submit an order to buy or sell if this number is negative SI dollars of the stock. Okay, and at the end of the day, so if you buy the stock, you get the dividend at the final date. So this is the trading profits of this guy if he submits an order SI. We're going to have frictions here, so you can think that these guys have a wealth constraint, or they have some short sale margin requirements they need to satisfy. So you cannot buy or sell infinite amounts. Okay, you are limited on how much you can buy and sell. So this parameter omega here captures these frictions. And so at the end of the day, since this guy's risk neutral, we're always going to be at the corners, right? The noise traders are going to submit some random orders for each firm stock and J. And then the total order flow here is given by the sum of the order flow of the informed speculators plus the order flow of the noise traders. And I'm going to denote by alpha J the mass of traders that learn about some stock J, okay, in equilibrium. Market clearing, it's very simple. I'm going to have a market maker. He observes the order flows in all firms. He doesn't know which ones are informed, which ones are uninformed, and then he meets those orders at the fair price. Okay, so he's competitive. But just to summarize here, Braz already summarized very well the timeline of the paper, but let me repeat. So first, the firm chooses this conservatism ratio of the manager. Then speculators make the learning decisions. They trade, the market maker meet the order, and then the manager invests after observing market activity. Cool. I'm not going to explain here the definition of equilibrium. This is very sturdy and perfect Bayesian equilibrium. I just want to emphasize this. We're going to focus here on symmetric equilibrium, in which all the firms choose the same compensation contract. Okay, that's the only non-standard thing we impose. Cool. So let me go to the equilibrium. I'm going to have to take some shortcuts here in the interest of time. But let me first say we define the paper some function xj that is increasing function of the aggregate order of stock J. Okay. And we're going to call this increasing function the aggregate order. It's just a monotonic transformation of the original aggregate order. It's a monotonic transformation that depends on the equilibrium strategies, but you don't need to bother about those details right now. And given this definition, end up that the strategy of the manager is very simple. He invests whenever this aggregate order is above his conservatism ratio that was chosen by the incumbent shareholders. Okay. And the idea here, so if this cutoff, if this conservatism ratio is lower, that increases the probability that this guy is going to undertake an investment, regardless of what the market tells him about this firm, which increases everyone's incentives to trade this stock J. What is the idea? You have information about the investment opportunity of the firm. But if that's a firm that has a very low probability of undertaking this investment opportunities, you have very little margin to make trading profits because you have information about an investment opportunity that's not going to be undertaken. So this information is not useful. So when the firm invests more, that boosts your incentives that you have to trade on your private information. Okay, so in equilibrium, that's going to happen. So this is already like a result I'm stating here. And then here comes the one of the results of the paper. I'm not going to be able to tell you the details of how we construct it, but I'm going to try to give you the best intuition I can. And the idea here is that when firms compete for market feedback, when they choose this managerial conservatism ex ante, we're going to have that in equilibrium. There's always going to be an equilibrium in which firms do not react to market information. Okay, so they're going to choose a manager that is very risk taker, that's not going to react to the market, even though the market's going to provide useful information for them. Okay, so those firms are going to be their stock traded in equilibrium. Actually, they're going to split the total number of traders is going to be split equally among those firms. They're gonna be some information on those prices, but the firms, given this ex ante decision, they're going to choose a manager that uses this information very poorly. Okay, and they try to do that to try to get more firm trade into the stock. But as all other firms are doing the same thing, in the end you fail, and you just end up not using the information that's out there in the prices for you. Okay, so here we want to emphasize this theoretical highlight that if you start in the model for a single firm, usually having your being able to have these managers overinvest is a good thing. You are able to learn more from the market, even though you distort a little bit the use of information. This is usually good. Here, it can be very bad. Okay, so this is the fact that you can commit to this can be very bad. And also here we have an empirical implication that if you observe a low investment sensitivity to stock price, that does not necessarily mean that there is little information in the stock price that could guide investment decision of the firm. It's just that in equilibrium, firms are choosing not to use this information as an equilibrium outcome. But this is a very stark equilibrium. Okay, this is like a very stark case. We have a more intermediate equilibrium. I'm going to explain in a while, but first let me try to explain a little bit why this rat race, why you have this bad equilibrium. And the idea here is that we have a rat race among firms to be attractive to informed traders. Okay, so let's say you have two firms. Firm one tries to get a larger share from trader than firm two. How are we going to do that? You be more aggressive in your investment policy. Okay, so you use information a little bit less efficient. You distort a little bit the incentives of the manager. You deviate from shareholder value maximization, but that's going to allow you to get more information. So you say, that's good. I want to do that. But now firm two is going to try to undercut you. We're going to say, you know what? I'm going to be even more aggressive. I'm going to still bring these guys to trade my stock. And then this process continues, and you may end up in this equilibrium where no one uses the information from the market. Okay, so it's sort of this simple equilibrium in Bertrand, where firms compete on prices and one undercuts the other. Here's a similar thing that's going on at the end of the day. Okay. Now we also have a good equilibrium. Okay, an equilibrium in which firms learn a little bit from the market. Okay, but still in that equilibrium, this equilibrium is still inefficient in the sense that they still use market information, but they use less than they should compared to a first best. Let's think about it like that. So there's always going to be an equilibrium where firms use information from the market. So this managerial conservatism is interior. Okay. But they do not maximize shareholder value. In equilibrium, they all obtain the same share from trading. So if all these guys could commit to say, look, let's just tell our manager, maximize shareholder value exposed, would like to do that, but this is not an equilibrium. Okay, so the message of the previous proposition still goes through, but it's not that extreme.
Caio.
Yes?
So I sort of didn't understand where the strategic complementarity is coming from, I think, if you could clarify that. I presume you have strategic complementarity because you have two equilibria, so if the others are doing more, and then you give an intuition there's more like a Bertrand kind of competition. But if you have two equilibria, then if you were stuck on the first one, if you can be stuck on the first one, then it's sort of strange that it's a kind of a Bertrand intuition, because the Bertrand intuition would take you down to the bad equilibrium, what do you call it, bad equilibrium.
True. You're saying yes. In a Bertrand setting, you would have one equilibrium with perfect competition. Here, yeah, here it's a little bit different indeed. The strategic complementarity here, I'm not sure I would call it the strategic complementarity, but the idea here is that you want to. So I mean, the more aggressive other firms are being in their investment strategy, the more incentives you have to be aggressive in investment strategy. Otherwise, you get a very little fraction of the market. Okay, so that would be sort of the strategic complementarity we get here. So I agree with you that is not. I gave the example of Bertrand, but perhaps this is not a good analogy, because here we have more stuff going on. At the end, you end up with this two equilibria. You may have other equilibria, right? Remember, here I'm focusing on the symmetric equilibria. So you also may have some equilibrium in the middle there that I'm not emphasizing here. So this is not the whole equilibrium set if you allow for more general strategies. I'm not sure I answered your question, Bernardo, but
no, you did. I'm still thinking that the other is I understand that if the other is investing more, then I'll get less attention. But then I'm thinking at the margin. I mean, so far I'm getting less attention, but then at the margin, investing more is not absolutely clear to me, and I'm sure this is my limitation, not your limitation, but it's not absolutely clear to me that at the margin I'll have even more incentives to invest instead of saying, okay, I won't get any attention anyway, so let me forget about it. But anyway. Yeah.
So perhaps this slide will help a little bit. I'm not sure I'm gonna directly to your point, but I think it may help a little bit with the intuition of at least why we cannot have all firms maximizing shareholder value in equilibrium. So what is the idea here?
I think this one I got. Go through it. But I think this one I got, so go through it.
Okay, so the idea here is the following. So let's say all firms are maximizing shareholder value, okay? That means that all firms are using this information in the best way possible, in the most efficient way possible, okay? But now think about a single firm. The single firm is faced with the following choice. I may distort a little bit the use of information, and by doing that, I'm gonna get more information, I'm gonna attract more traders to my stock. If I'm at the first best with the best use of information, this marginal distortion in the use of information by this envelope reasoning is close to zero, right? So I always find optimal to do this deviation and deviate from shareholder value maximization. So that's why I cannot sustain shareholder value maximization as an equilibrium. It's a simple envelope theorem reasoning I'm doing here. Okay, so I'm not sure that answers another question, but that's the intuition. Cool. We have some comparative statics. Let me see how I'm doing on time. I'm going to try to end up early, so I'm not going to explain this. Let me just explain this first one.
Sorry, can I just try to complement your answer to Bernardo?
Yeah, sure.
No, I was just thinking that, Bernardo, if you start from this shareholder value maximization, you don't want to do that, so you go to this other interior equilibrium, right? And that's stable, let's say. And then if you do a best response iteration, if you would start a little bit to the left of this equilibrium, oops, I'm sorry, I have a baby here. You would also come to this equilibrium. But if you start the best response iteration further to the left, at some point you go to this extreme equilibrium. So both equilibrium is stable, and there is another equilibrium there in mixed strategy. Sorry.
Okay. So today is a public holiday in Chile, so we're both at home with the baby. Cool. All right. So let me quickly emphasize this this comparative static here. So when you increase the mass of informed speculators, so there's more informed traders in the market, firms have more incentives to distort the managerial decision. The other comparative statics, they sort of go in with the same idea here. We also have this comparative static on the number of firms. So let's say increase the number of firms, how that should affect the distortion in the managerial decision. As you increase the number of firms, first you distort more the manager decision. and then at some point you distort less. Intuition here is the following. When you have more firms, you have more guys to compete with. So you want to be more aggressive in your investment policy. But on the other hand, you're also reducing the number of speculators per firm. So there's less potential that the market's going to tell you something useful. So we also have less incentives to distort to manage your decisions. So these two effects are there. For low values of J, one dominates. For large, the other dominate. The common paradox here, it's very simple. We just say that if you could commit to a policy, all firms could commit to enforce shareholder value maximization, everyone would be better off. Everyone would end up with the same share of informed trading, but they would use this information in the most efficient way. So this would be a good thing. Okay, so this is what we call the commitment paradox, the fact that you can commit to this investment policy ex ante ends up being bad for you. And then we look a little bit to IPO. So let me quickly explain that in 1 minute. We extend the model to allow firms to be now decide whether or not they want to be public traded. If you are public traded, you need to pay a cost. Okay. To make things interesting, we assume the good, which it's also not the best, it's not efficient, but the best equilibrium in the model we assume is played. Otherwise, firms will never pay this cost to be public traded since there are no benefits. And basically, what we show here is that a social planner, he would, when deciding whether or not to put an additional firm in the market, he would look at two things. He would say, look, if I put an additional firm in the market, I reduce how much information there will be for the others, but this firm benefits from the information it gets. Okay, and also when you put another firm in the market, given this comparative static here, depending on where you are, you may exacerbate this inefficient channel I've emphasized throughout the paper. So the policymaker will take those things into account. The firms don't. So if the policymaker wants to implement the first basket, you would have to tax the firms that go public. So you want to impose a per given tax on IPOs because there's always a negative externality on others that firms end up not internalizing. Cool. So that's the paper. So I propose this model of multiple firms or firms learn from the market. We showed that this the fact that firms want to attract informed trading to the stock, they want to be attractive to traders, may make them take decisions that are inefficient and eliminate the potential of increasing their efficiency through the secondary markets. And then the centralized equilibrium firms choose not to maximize shareholder value, but collectively they would like to do so, which would be good for them. And with endorsements publicly listed, too many firms go public. So that's what we have in the paper right now. We are revising it. Perhaps the motivation changed quite a bit, but if you have any comment on that, I'm happy to hear. Thank you.
All right, Caio, we have 1 minute for additional questions. If there are any questions.
I just one, sort of okay, Caio, go ahead.
Go on.
Yeah, I already
no,
talked
don't
too
worry.
much.
no,
it's just go ahead.
Right. So can we briefly go back to what you said, that if the speculators could also buy could also get a share of other firms, and they don't have this hypothesis, this assumption of they have very limited attention. You said that it was without loss of generality, right? But I was thinking about, well, if you have a small number of firms and they all have different fundamentals, and suppose that you could pay to know the information of 2 or more firms, then what you see in the market might also reveal information about the fundamentals of the other firms. And then this somehow might have some influence on the firm's information strategy. Do you think that's an interesting avenue to expand upon the paper, or you didn't thought about it?
No, actually, we thought about it, Caio. This is a very good question. We thought about it. We could have some correlation about the fundamentals of the firm, right? Here they are completely uncorrelated because we want to focus on this competition channel. We conjecture the results. They don't depend as long as this correlation is not. I mean, we conjecture the result does not depend on that. We conjecture what is important is that there is some firm-specific information for you to learn from the market that is specific to your firm. This is important. Now, there could also be information that is common to all the firms that you could learn from the market. We thought a little bit about it. We think this is if this was there in the model, we think things will not change that much. So we could perhaps allow for the two things. But the key assumption here is economically is this. I want to learn about something that is specific to my firm. If I only want to learn about stuff that's common to all the firms, that's like an aggregate variable of the economy, then yeah, you have less incentives to compete because you can learn from the others. And you're completely right on your intuition. Yes.
Good, thank you. But as you still have some time, we will present in 25 minutes. So if you have a quick question, you.
Mine was just a way more mundane question. It was just because here I understand the focus on symmetric equilibria, and of course that you probably have asymmetric equilibria as well, and of course a type of asymmetric equilibria where firms kind of sort themselves into some firms that actually they just go for the x upper bar minus infinity, and the other ones kind of compete for, I don't know if that's, and anyway, I was just trying to understand more the sort of structure of the equilibrium, and whether makes any sense to consider, is there any interesting asymmetric equilibrium, something that by considering asymmetric behavior is actually going to lead from some different insights than what you have right now?
Yeah, in 30 seconds, perhaps, I think there is some interesting thing to look at here. Perhaps, I mean, if I allow firms to ex-ante be different in some dimension, I mean, even if they're equal, there may be a symmetric equilibrium. But now let me go one step further and say, no, let's say there's some ex-ante difference about the firm. Perhaps this model has something to say, okay, which firms end up being traded in equilibrium, which firms end up not being traded. And perhaps once we understand better the symmetric equilibrium, we could answer this type of question just thinking out loud here. So I think there's something interesting there, perhaps.
All right, thank you, Caio. So for the last part of the session, we will discuss, well, my paper. We're gonna talk, let me just share the screen here with you. So can you all see it? Right, let me just change the way that I'm viewing, so, right, so then I can view all of you. Can you see it?
Yes,
good.
Can see.
All right. So yeah, so we're going to talk about, let me just see if I can, yes. All right, so we're going to talk about bad reputations with rating systems, and this is joint work with Professor Daniel Monte. All right, so people rely on online reputation systems for a variety of daily activities, right? So rating systems help consumers choose their goods, but rating systems also help fulfill clients' requests for expert services. So prior to visiting a doctor's office, patients can check physicians' ratings and reviews at RateMDs. Students can select courses according to teachers' evaluations from other students at Rate My Professors or Rate My Teachers. Americans can hire, rate, and reviews home service providers on Angie. And drivers can find the best rated mechanics all around the world on Yelp. So when dealing with online reputation systems, experts being rated, they can act strategically to influence their ratings. And let me illustrate this point with a specific example. So consider an online reputation system for physicians, a doctor with an online feedback record on it, and a patient with a physical discomfort. The patient cannot perfectly ascertain his true needs, so he relies on the physician diagnosis if he goes to her clinic. So suppose that upon examining the patient, the physician correctly learns that the problem requires a high-cost treatment. Well, because the patient cannot ascertain his needs, he cannot be sure that the high-cost treatment is adequate. And if he believes that a low-cost treatment would be effective just as well, he might review the physician as an expensive one. So the physician might propose a less costly treatment instead to avoid bad evaluations being posted online. And this is bad for the patient. But suppose now that the physician correctly learns that the problem requires a low-cost treatment. Again, because the patient cannot ascertain his true needs, he cannot know which treatment is correct. If he believes that this problem is a serious one and would require a more complex, more costly treatment, then proposing a low-cost treatment could lead to the physician being badly reviewed as negligent. So the physician might propose the wrong treatment instead, and this is just as bad for the patient. The platform can act against this perverse reputation effect, but how to tackle this issue is non-trivial. It could, for instance, strategically censor some past information or come up with a scheme to benefit service providers. But now customers know that the platform is not being fully transparent, so they might look at past feedbacks as deceptive. So for those reasons, the benefits of such mediated interactions, they could be limited. Our question is, to what extent? How can online reputation systems contribute both to experts and customers' value from their interactions? And we discussed this specific example in online physician-patient interactions, but the benefits of studying optimal reputation systems can be found in many other areas. For instance, professors sometimes avoid being rigorous because they are afraid of getting bad reviews from their students. So another example, mechanics are known to have a reputation for being expensive, so they might propose a low-cost tune-up to motorists, even when the adequate repair would be a costly engine replacement. So our environment is a stylized interaction between a long-run expert and a sequence of short-run customers. In each period, a customer has the option of hiring the expert's services. If hired, the expert observes a problem and proposes a treatment. I need someone here. Right. A severe problem requires a high-cost treatment, and a mild one is solvable through a low-cost treatment. The customer, however, cannot determine how severe the problem is. Moreover, each customer has a common prior that the expert is a bad commitment type that always provides the expensive treatment. So for those of you familiar with the reputation literature, our benchmark setting is the bad reputation model in Jeff Ely and Valimaki's paper, which is called bad reputation. And this setting is particularly interesting because without any information designer or any sort of information censoring of the expert's past actions, they show that the reputational concerns are so strong that either customers only rarely hire the expert, or the market ceases to exist altogether. Thus, in this setting, information censoring might improve efficiency dramatically. And the class of information policies we consider is called a rating system. So what is a rating system? A rating system consists of a finite message space, an initial distribution over messages, and a transition rule, mapping the current message and any possible observable outcome, say high treatment, low treatment, no treatment at all, to a probability distribution over the message space. Technically, information policies in our model are finite automata. Empirically, one can think of them as rating systems commonly observed in many online reputation systems, star rating systems. Importantly, our information setting assumes that the current rating is the only source of information for each customer. And here is why we feel that this is a reasonable assumption in this environment. First, we want to capture complexity issues that platform faces when dealing with huge amounts of data. Second, it better represents the way in which customers draw their inference from such relationships. So think of it as customers' choice between observing a summary statistic of past data or keeping track of all possible histories of treatments in the exact order. Third, it is meant to be a plausible account of the way that platform users consume available data. We have gathered consumer surveys showing that the star rating is the most or the second most important factor in online reviews that consumers pay attention to when judging a business or a product. So we are restricting the class of policies a platform can design. So yes, there will be a constraint on what the intermediary can achieve with a rating system. But we characterize the upper bounds on the experts and customers' equivalent payoffs, and we construct rating systems that reach these upper bounds. And we find that to maximize customers' value from the mediating interactions, then the number of ratings in the higher the number of ratings in the system, the closer the payoff will be to the upper bound we derive. However, in equilibrium, the system is almost never in intermediary ratings, say rating 2, 3 out of a 5-star rating system. So in other words, rating inflation arises optimally in our model. And this is consistent with what is empirically observed on popular rating systems. And we also find that intertemporal concerns matter for the construction of the optimal system. That is, we must consider experts' discount factor when constructing the transition rules between ratings. In general, the higher the discount factor is, the more we must make transitions between intermediary ratings independent of the choice of treatment. So there is also a rating persistence pattern arising endogenously here. And here's the intuition. The more the expert cares about being caught in extreme ratings in which customers higher her incentives to game the system by providing inadequate treatment. So a transition that depends less on the expert's actions, it alleviates perverse incentives. And we also show how to maximize the expert's value from the interaction. To do so, we only need 2 ratings. The optimal system is a significant improvement in comparison to both the non-censoring and the full censoring environments. And in this optimal system for experts, there is no bad reputation effect, and the expert is often hired in the long run. So the outline of today's presentation is as follows. I'll present the model, I'll discuss the relevant results without any information policy. Then for today's talk, we will focus on deriving optimal systems for customers. We'll start the analysis with binary systems so that we gain intuition, and then I'll discuss the main results for a system with multiple ratings in it. Right, so here's just the representation of the stage game with a strategic expert. So in every period, a nature selects a customer's problem, which can be a major problem or a minor problem, both with same probability. And without knowing his problem, he chooses whether to hire the expert, out or in. And if he hires, then the expert diagnoses the problem and proposes a treatment, which can be a high-cost treatment or it can be a low-cost treatment, right? Customers get a positive payoff whenever the proposed treatment is adequate and negative otherwise, okay? A major problem requires a high-cost treatment and a minor problem requires a low-cost treatment. And we assume that payoffs are such that if the customer believes that the expert will propose the treatment independent of the problem, then this consumer would not like to hire the expert. But note that the expert has the same payoffs as the customer in the stage game. So she wants to provide the correct treatment, at least in the stage game. The expert could be bad as well. Now, a bad expert is one that always provides the high cost treatment, independent of the problem. Neither the platform nor the customers know if the expert is strategic or bad, but they all share a common prior belief about it. So in a one-shot game, the expert tells the truth and the customer hire if the expected payoff from doing so is higher than the outside option of not hiring. So this generates a belief threshold above about the expert being bad. Above it, not hiring is best for a customer. So if this game was repeated and customers could observe past treatment choices or lack of it whenever there is no hiring, if the prior belief is above the belief threshold, then the first customer would not hire, no information would be generated. Then the second one would not hire, no customer will ever hire in this case. But what if customers start with a low prior about her being bad? Then from Jeff Ellis and Valimaki's paper about bad reputation, we know that in any Nash equilibrium of the game, as the expert gets infinitely patient, her long run value from the interaction is 0, which means that she gets hired at most rarely. Now, here's a brief intuition. At every period, hiring is possible only if the expert is playing the correct actions with positive probability for every problem, including the high cost treatment for the major problem. So this implies that the next customer's posterior belief about the expert being bad is going to be increasing period in the past period prior belief. Thus, a long sequence of major problems will inevitably lead to a posterior surpassing the critical level, above which not hiring is optimal choice for customers. So if the expert is very patient, then she cares more about future payoffs, which will be 0. But then the expert might have incentives to propose a low cost treatment instead. so that she can review herself to be good. Now, rational customers anticipate this movement and they will stop hiring the expert altogether. So in either case, as the patient gets infinitely paid, as the expert gets infinitely patient, the long run payoff for every Nash equilibrium will be zero.
Caio, can I ask a clarifying question? Yeah. Perhaps I'm
sure.
Something. If I take my car to the mechanic and he offers me a high cost treatment that was not needed, probably I will never find out because I don't know the counterfactual, what would happen to my car if he didn't provide. But if he offered me a low cost treatment and I needed a high cost treatment, in 2 weeks I will find out, my car will break, and etc. That's not captured here, right? This asymmetry, or is it?
No, it is not. You're right. We have a symmetry between high cost and low cost treatment, but most importantly, I think, is what you observe in the past history is actions, not necessarily the outcomes, right? So it is you observe whether the mechanic has a history of providing the high cost treatment or providing the low cost treatment, a tune-up or an engine replacement, but you don't necessarily observe the history of the outcome, in a sense that you don't observe the payoffs, right? So that will change a bit if we could do so.
Okay, thank you.
All right. So, well, there's a trivial way to avoid bad reputation. We just simply shut down every possibility of observing past actions. The online platform could just censor absolutely all information from the past. So then every current customer would play a game as if there were no reputational concerns for the expert. Well, the problem with this is that, okay, it does not tempt the expert to lie, but it does not bring any additional benefits to the customers relative to the stage game either. So the question is there a rating system that improves upon these extreme cases? Or what is the optimal rating system? But first things first, what is a rating system? Well, broadly speaking, a rating system is a rating set and a Markov map from ratings and signals to a distribution over ratings. In our model, the bad reputation model, signals are the treatments, which are endogenously generated by the expert choices whenever hired. Okay, so since each customer's only source of information comes from the observation of a rating, they must all have the same hiring probability alpha at every rating. Since customers do not observe past treatment history, we consider the expert strategy as a map from ratings and problems to treatment choices. And we can divide the strategy in terms of the probability of providing the correct treatment, a major problem or a minor problem. And we also can define a probability of observing the common treatment, the high cost treatment between the strategic and the bad expert, this gamma here, and a probability of getting the adequate treatment in every rating, this beta here. So given any rating system, the probability of moving from one rating to another for every type of expert will depend both on the customer's willingness to hire and the expert's choice of treatment. Well, because the bad type always plays the expensive treatment, this is the only signal that she will convey. So we have a stationary rating system and we have a stationary strategy for the agents. So we will induce Markov transition matrices defined over this rating set. Because there are two possible types of experts, there will be two transition matrices, one for each type. And for this talk, we will assume that all ratings will be visited in equilibrium by at least one expert. But in the paper, we show that this is without loss of generality. Technically, we are focusing today on irreducible Markov chains, for which we know that there will be probabilities for each type of expert visiting each rating infinitely often, okay? So knowing these stationary distributions in equilibrium, customers will infer something about the type of expert after observing each rating. And we assume that they update beliefs in a Bayesian way using the stationary distributions. So what is an equilibrium here? Well, an equilibrium is a rating system, a strategy profile, and beliefs such that, one, customers are doing the best they can given their beliefs, and beliefs are consistent on the equilibrium path. And two, the strategic type of expert is doing the best she can at every rating after observing each type of problem. And for every equilibrium, customers pay off is just the expected payoff they get in every rating, weighted by the stationary probabilities of them finding themselves in every rating. And what we are interested in is finding a rating system and an equilibrium that maximizes customers' equilibrium payoff from this mediated interaction. So we will examine what we can achieve with a binary rating system right now, but I can pause a bit and have some time for quick questions. Are there any? All right, good. So we shall proceed. Right, so in the paper, we prove that with a binary rating system, only 2 ratings, in which there is hiring in rating 2, but there is not hiring in rating 1, there will be an upper bound, this whole upper bar here, on the highest possible posterior in equilibrium. So why this is the case? Well, customers will only hire in rating 2 if the expert is willing to provide the costly treatment with some positive probability, right? So if he's willing to be honest about the major problem with some positive probability. But then this means that it is not possible to avoid the strategic expert from visiting rating 1, the non-hiring rating, because the same signal that identifies the bad expert also is being generated by the strategic expert. So the fact that one signal is being played by both types, it also implies that there will be a lower bound on the lowest possible posterior. And this is the case because there must exist a positive transition out of the non-hiring rating to the hiring one. Well, otherwise the strategic type of expert will be caught up in rating 1, and there would be no reason not to hire in rating 1, right? So because the belief spread is limited, right? The maximum belief spread we can achieve with a binary rating system is limited. Then there will be a limit on what we can achieve with a rating system. And this limit is just this dashed line here. The red line is just the one shot, the payoff from the one shot gain, right? And if we were to consider the repeated gain, we know that for every prior belief, the value of interaction would be 0 because the expert will not be hired in the long run, right? So even with 2 ratings, a binary system, we improve upon the no censoring and the full censoring frameworks. So, right, we found an upper bound on customers' equilibrium payoff, but can we actually construct a system that achieves this upper bound? Well, we can, if we can generate the maximum belief spread between rating 1 and rating 2. And to do so, we need to split the possible cases in 2. The first case is the prior is below the belief threshold, above which not hiring is optimal. And this means that in a one-shot game, a customer would hire the expert without any additional information. So in equilibrium, we need sometimes to recommend customers not to hire the strategic expert by letting her rating change from 2 to 1 after the observation of a high-cost treatment, but not always. So this will ensure that the bad type of expert will visit the rating 1 frequently enough to justify not hiring in it. And the second case is when the prior is above the belief threshold for which non-hiring is optimal. So this means that in a one-shot game, a customer will never hire the expert without any additional information. So in equilibrium, we need to downgrade the expert after every observation of a high-cost treatment, so that customers believe that it is more likely to have a strategic expert in rating 1, justifying hiring in it. And note that to do so, we also need to let bad types visit rating 2 sometimes, but not always. All right, so, okay, the system we construct only works with the strategic expert if the strategic expert is willing to tell the truth whenever hired. But will the system generate the right incentives? Yes, we show that in fact for any binary system it's optimal for the strategic expert to be honest whenever hired, right? So now we're gonna discuss multiple ratings. So just as we prove that there is an upper bound on the highest possible posterior in equilibrium, we prove that this bound persists with multiple ratings. And the intuition is just the same. Suppose there's only one rating of non-hiring, say rating 1, and we only need one non-rating because no information is generated at non-hiring ratings. So one rating for this class is sufficient. So for every hiring rating, the strategic expert must be willing to provide the correct treatment with some positive probability, but this means that at every positive transition from hiring ratings to non-hiring rating, there is a positive probability of the strategic expert being downgraded. That's why we have this bound, right? So the binary system, we showed that it actually constrains the lowest possible posterior that could arise in equilibrium. With more ratings, we can make this lowest possible posterior in equilibrium arbitrarily close to zero, right? So why is the case? Well, assume that we can arrange ratings in a decreasing order of posterior magnitudes. So say rating 1 is the highest belief, high enough that customers won't hire in it. Rating 2 is the second highest, low enough to justify hiring it. Rating 3 is the third highest, and so on. So what we would like to have is the lowest possible posterior about the expert being bad, almost close to zero, and the strategic expert telling the truth whenever hired in it. And we also would like to have the highest posterior belief about the expert being bad equal to the upper bound we derived, right? So we want to have the maximum belief spread. And we can do so by letting the intermediary ratings being downgraded with a higher probability under high cost treatment and upgraded with a higher probability under a low cost treatment, right? So with more ratings, we will have the bad type of expert getting caught in lower ratings. So this will lead to an upper bound on the customer's equilibrium payoff, which is just this dashed line here. So we improve upon the binary case, right? So the same question here. Can we actually construct a system that achieves this upper bound? Well, we can construct a finite irreducible system that does not exactly reach the upper bound, but it gets arbitrarily close to it, okay? And in this system, we can manage to have the expert telling the truth whenever hired, but this is not so easy as in the binary case, because it is not true anymore that the discount factor will not matter for the expert's optimal strategy, okay? Now, a quick intuition of why this is the case. Well, remember that we are looking for rating systems in which posteriors are in decreasing order of magnitude, right? And there is no hiring in rating 1. So when designing the system to maximize, we want to have the maximum belief spread, okay? And we also would like to have the experts stay most often at extreme ratings, because this is the highest possible belief spread we could get. So this is just the rating inflation pattern we see in real rating star systems, and it arises endogenously in our model. Okay, so we can manage to do so if we let ratings being upgraded with a higher probability under a low-cost treatment, but this comes at a cost. And what is the cost? The higher the expert discount factor, the more she cares about being caught up in the extreme ratings in which customers hire. So she has incentives to provide a low-cost treatment, even though this is inadequate, so that she gets caught up in the extreme rating in which there is hiring, right? So how do we work? How do we solve this? We make transitions between the intermediary ratings less frequent as the discount factor arises, right? So if we carefully choose the transitions out of the extreme ratings and between intermediary ratings, we can ensure that the posterior in extreme ratings will be well-defined and will satisfy the maximum belief spread we derived, even if the discount factor gets close to 1, okay? So in this case, the rating system involves the expert being hired in equilibrium and telling the truth, okay? And just to have a comparison, this is fundamentally different from what we saw in Ely and Valimaki's paper, because right now we have a positive value of interaction, even in the long run, right? So what we have discussed is just an intuitive understanding of the part of the proof of the following theorem, which is central to our paper, This is the last slide, and then I'll jump to conclusions. It says that for every prior belief below the belief upper bound, for any expert's discount factor, and for every positive epsilon, there exists a minimal number of ratings, and there exists a rating systems with at least this minimal number of ratings in it, such that the customer's payoff gets epsilon close to the maximum payoff we derived. In the system, the customer is higher in every rating except 1, and the strategic expert has the right incentives to tell the truth whenever hired. All right? So let me briefly conclude. People rely on online reputation systems to hire experts, but such systems can generate wrong incentives for experts and could also generate mistrust from customers, right? In the benchmark setting of Eli and Valimaki, without any information restriction, the expert cannot avoid being rarely hired in equilibrium, since either the belief about him being bad is eventually high enough so that customers no longer hire, or the temptation to reveal himself is so strong that the market ceases to exist. What we show is that there's, okay, with a rating system, there's a bound on the equilibrium payoffs, and we characterize it in terms of the posterior belief spread, but bad reputation is avoidable. That is, in equilibrium, the strategic expert tells the truth whenever she's hired and gets hired with positive probability, even in the long run. And we also construct such system, right? And the system is consistent with the rating inflation pattern we see in everyday rating systems. And it has this sort of rating persistence in a sense that we have to take it into account the expert's discount factor when coming up with the optimal system. That's it. I'm not sure if I have time to answer questions. So if some of you in the audience would like to comment on the presentation on today's talk, you can reach me through my personal email. Thank you.
Thank you, Caio. Can I ask you a quick one, perhaps? Or I don't know.
Sure, yeah.
Just how does it work? My question is more practical. In practice, how does it work, the rate inflation thing? How do you implement that? I mean, is there an example of some service using it?
Right. Okay. What we have, our optimal system. So let me first answer on a theoretical viewpoint, and then let me then answer on what we observe in rating systems, right? So our system works like that. We want to have two ratings in which experts will be caught up, and they will represent the maximum belief spread. So think of 1 and M, right? And we want to make the transition between intermediary ratings so that even though the probability of getting out of 1 or out of M is almost close to 0, the way that we change the parameters, the beliefs were going to be well defined, right? So what we would observe would be something like that. A high mass of observations on rating 1, a high mass of observations on rating 5, and some few observations or some few classifications on rating 2 and 3, right? So this is the theoretical answer to your question. Now, the empirical answer to your question. What we observe when we check, say, Uber ratings or other ratings, eBay's rating of sellers, we do observe a high mass of ratings on 1, 2, but most of them in 1, and we also observe a high mass of them in 5. But the number of observations for one seller or for one service provider in intermediary ratings, it is very small in comparison to the extreme ones. So what we are saying is that the optimal system endogenously generate what we observe in data, right?
In the data, you have like I mean, I don't know if Uber censors the rating, but in the data you observe sort of decentralized equilibrium, right? Not necessarily the optimal. That's more of my question.
Yes.
Or does Uber does something with the ratings and to achieve that? That's why I didn't understand very well the comparison, I think.
Right. Yeah. Yes. You're right. What we have here, we are trying to optimize, but we are trying to optimize, at least for what I presented today, for customers. So it is as if we were assuming that customers choose optimally which rating system they would rate a service provider, right?
Okay.
In some sense, we could think of what we observe as, I'm not saying that is the only explanation of why we have the rating system. There are many other explanations, and I'm not saying that this is the best one, actually. But this is just another explanation on why we would observe this pattern of rating inflation in data.
Okay, okay.
But rating inflation is not a property of the mechanism, it's an outcome, right? Is the optimal mechanism generates rating inflation, right?
Right. But I mean, when we construct the system, we need to have this in terms of, we need to have a high mass of periods, or we must have experts visiting extreme ratings infinitely often and not visiting that much the intermediary ones. Does it make sense?
Yes, yes. So one thing that I was thinking just in terms of the motivation. So the part that you go to the mechanics, you have you think that the thing will cost low, and the mechanics says, oh, it's much expensive, then you are suspicious. The other case that he does the opposite thing, to me seems a bit less natural in a sense. You know what I mean? That going there, you want him to charge you high because you think your problem, and then he charges you low and you are pissed off. That to me is a bit less natural. So there is kind of an asymmetry to me in the two things. But yeah, that's how I felt. So I'm not sure. Right.
Well, empirically, I think you're right, and this connects with the Caio's question, because we are assuming symmetric structure in terms of payoffs. But one thing is that we are assuming this, especially because in Jeff Feely and Valimaki's paper, and they also have the symmetry, we have a very extreme result, right? In the sense that the market ceases to exist altogether because the bad reputation effects is so strong. So we want to use this as a benchmark because we want to see what we can do if we censor information in an optimal way. So one thing is we want to use this environment in which assumes symmetry because we want to see how can we reestablish market efficiency here. The other case here is, well, this is the analogy that I like to do. So is that maybe the mechanic is not the best explanation here, but think of a physician. I like the idea of going to a physician, and then you believe that you have a really, I don't know, suppose that you have a pain on your chest, and you believe that is very serious, right? So the physician examines you and see that you don't have a serious problem. You just want to, maybe you are just stressed out. Maybe you want just to get back to your place and rest. And if you observe reviews, you will see that some of patients don't like that because they believe that either the doctor is negligent or the doctor is not good or the doctor does not pay attention to their problems. So sometimes you would also like to have a high cost treatment so that you don't want to be reviewed as a negligent physician. Right?
I see. So you do observe that in the data. That was kind of my worry. Okay, so that's nice. That's fine. Thank
you. Let me stop sharing. So if there are no questions, I think Diego, right? Diego is gonna close the Zoom meeting. I thank you all for being here. It was great presentations, great talks, and I hope you enjoyed the conference.